Welcome back. We're now into chapter 5. We just finished up 410, which was finding the antiderivatives, and now we are working on area and distances. Our objective for this lesson is to determine the approximate area under the curve and find the distance traveled by an object traveling at a varying speed. So that second objective, the distance, will be an application of area. So the first thing we're going to do is we're going to look at just the area problem and knowing how to calculate the area of certain shapes that we have. And we're looking at the rectangle and trapezoid. So the area for a rectangle, we know, is base times height, and we also know the area for a trapezoid, the height here, and we have a base 1 and a base 2. So it'll be base 1 plus base 2 divided by 2, or the average of the bases, and then we multiply times the height to get the formula. So common for all of you. And then now for the second one, you could stop your video and find the area of each of the shapes that are shown if I designate the units on the rectangle and trapezoid as being units of velocity and then time. So try that, pause the video. And now that you've had a chance, check your answers. So for this one, we have a base that's equal to 5 hours, that here, and we have a height that's equal to 65, and it's units of miles per hour. So when we multiply those together, we have base times height, so base times height is then equal to 65, or actually, I'll just leave the 65. Height times base is 65 miles per hour times 5 hours. Cancel the hours as units, and we're left with 65 times 5, or we have 135. Oh, sorry, 325, I mean, where that came from, 325 miles. So interesting, when we get units of miles for area, we often think about area being in 2 dimensions, should be like miles squared, but in this case, we're using area to model our answer. So a trapezoid here, we have the base and the height. So we have the base is 10. I'll just put the numbers here, 15. And then the height of the trapezoid would be the perpendicular distance between the two bases. So that's 6. So we have the following. We have 10 plus 15, and that would be in meters per second. And that would be divided by 2, and then we would multiply by 6 seconds. So if we did, then we would then get 25 meters per second times 3 seconds. When we simplify, 2 goes into 6 3 times. So when we finish, we get 75 meters for our final answer, as the seconds will then cancel when we multiply the 3 seconds times the 25 meters per second. So we get our answer in units that appears linear, but in fact, we're using the area idea to model the rate times time. So then, in considering the polygons below, we can find the area by dividing the polygon into triangles, of course. So if you look at this first image, so we can find the area by finding the sum of the parts, and we would say, okay, area 1 plus area 2 plus area 3 plus area 4, and that would give us the area total. The area total then, of course, would be, we would just add them all up together. Area 1 plus area 2 plus area 3 plus area 4, and you remember from your Algebra 2 or pre-calculus class, that if we were going to find the area total, sometimes we would even put some notation with it that would look something like this with that Greek letter sigma, the sum from I is equal to 1 to 4 of A sub I, where I is the counter, and then that would give you the total area. So finding the whole by adding up the parts, as we did with the triangles there, the Greeks use a method called exhaustion. It kind of implies that you get kind of tired when you're doing it, I guess, but exhaustion, in which they added up smaller and smaller triangles to find the area of a circle. So if we considered that we have a shape that you see here, that we would really have 4 triangles that we would find in here, we could find the area. And if the Greeks wanted to find the area for a circle, it would equal the limit as the number of triangles would then go to infinity, or the number of sides, if they wanted to find the area for any polygon, would go to infinity. It would approach the circle. So this would be the area for a circle, because a circle by definition is a polygon in which the number of sides has gone to infinity. So the Greeks used that method where they decided that they could find the area of an irregular shape, or a shape that they couldn't find the area for, and then they would take it down to where they would make infinite subparts to that. So what we're looking at in this chapter is that we want to find the approximate area under the curve, sometimes in an irregular shape, and also interpret it when the dimensions are velocity and time. So first we take a simple graph that we often use in mathematics because it has such a very simple and nice, smooth appearance. Y is equal to x squared, or f of x is equal to x squared. So what we're going to do in the first example is we're looking at using rectangles to estimate the area. We want to estimate the area under the curve of the parabola f of x is equal to x squared from 0 to 1, pictured below. So you can see we have 0 to 1, and it looks like we have 4 subdivisions. So the area of each rectangle is, well, we want to have the number of rectangles. This is going to, our first rectangle is a sub 1, area a sub 2, a sub 3, and then a sub 4 as we go across. So the area of each rectangle, if it was given, would be, well, think about this. We need the point on the right-hand side, since this is a right-hand estimate for rectangles of equal length. So we know that their width is the same, but we need the value for their height. So if you look at the point on the first right-hand endpoint, we have the x value of 1/4, and since it is the function x squared, we're just going to square the x value to get the y value, which would be 1/16 for the first point. For the second point, we have an x value of 1/2. When we square that, we get 1/4, so the height is 1/4. The right-hand side is 1/4 for the height. And then for the next point, we're going to take 3/4, the x value, we're going to square it, and we're going to get 9/16. And then the final right-hand endpoint, we have 1/1, so that we know, for instance, that this height on the end is equal to 1. So what we would need is we would need each rectangle, we would need a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. And what we're going to be producing here is a R4, which we use R4 for the right hand with 4 subintervals, the right hand approximation for the area under the curve. So to get the area, we would just say, okay, base times height, so it's going to be 1/16 for the function value times 1/4, plus the next height is then going to be the one that I have blued out there. It's going to be a height of 1/4, and the width of that rectangle or the base is 1/4. Plus, then I've got 9/16 times 1/4, 9/16 for the y value, times 1/4, the base or the width. And then we have 1 for the height times 1/4. Now you can kind of see if each term has a factor of 1/4, it may be easier in the long run if we took this and said, well, we'll just add up the y values, 1/16 plus 1/4 plus 9/16 plus 1, and then multiply by 1/4. And that's what we'll do in the next example. So when we do this, we add everything together and we get that the area is approximately 15 30-seconds. 15 30-seconds, and I'll leave that up to you to put that in a calculator to divide, okay, to get that approximate value. So you can see it's somewhere a little less than a half for the area, but you can see that this is an overestimate. So box that up. This is an overestimate because you can see that we have some area that's above where I'm putting the dots. There's a little bit of extra area there that takes us over what the actual area would be. So I'm going to pause the video right now at this time, and we'll pick up at the second video for 5-1.